Hi everyone. In this video, we're going to look at some more complicated examples of partial fractions. Here's the first example. Find the PFD of this proper rational function. We know the first step is to completely factor the denominator. So let's take a look at this quadratic expression and ask ourselves if it can be factored any further. It turns out this one can't be, as shown by a quick check that the discriminant gives us a negative value. And so the expression given to us is already completely factored, and we can move on to the next step. This is where we make our prediction about what the PFD will look like. In this case, we only have one factor to account for in the denominator, but we notice that factor is raised to the power of 2, meaning we need to build two partial fractions for this factor. Our first fraction would have an exponent of 2 in the denominator, while our second fraction would have an exponent of 1, according to the discussions from the previous video. Next, we need to predict the form of the numerators, and that's done by going back to the definition of partial fractions. That definition shows us that when our fractions come from an irreducible quadratic factor, such as these ones, our numerator should be linear. So my numerators here can be called ax plus b and cx plus d, respectively. And all that remains now is to solve for these constants. For that, we know it's easiest if we eliminate the fractions by multiplying the common denominator to both sides. And you could pause here to check that this would be the result. At this stage, I would normally suggest plugging in easy x values. In this case, there aren't any x values that would eliminate terms on the right-hand side, and that's okay because technically any x values can get the job done. But instead, I'm going to show you an alternative method that I like to use in these types of situations. Rather than plugging in x values, we're going to expand and compare coefficients. So let me show you what I mean by that. When I say expand, I'm referring to multiplying everything out on the right-hand side. So you can pause and check that you'll get these results after expanding. And next, we're going to compare coefficients. The idea here is that if the left side really does equal the right side, then the coefficients on the left need to be the same as the coefficients on the right. So for example, let's consider the coefficient of x cubed. On the right-hand side, there's only this one term that contains x cubed, so the coefficient of that would be c. Now let's look at the coefficient of x squared. Well, there's two terms here that both contain x squared, so if we collect those together, we can find that 2c plus d is the coefficient of x squared on the right side. What about the coefficient of x? Well, there are three terms here that contain an x, and collecting those together shows that the coefficient is a plus 4c plus 2d. All that remains now is the constant term, which would be given by collecting these remaining terms together. Now let's see if we can also identify the coefficients on the left-hand side. Notice that although we don't typically write it, x does have a coefficient of 1. We can consider x squared to have a coefficient of 0 since that term isn't even there. And similarly for x cubed, we can consider the coefficient to be 0. And now that we've identified all the coefficients, we can compare them. So we'll start with the coefficient of x cubed. We know the coefficient on the left must be equal to the coefficient on the right, showing us that 0 equals c. So we've made progress in solving for these unknown constants. Next, let's compare the coefficient of x squared. That shows us that 0 equals 2c plus d. But we've already shown that c equals 0, so this expression can be simplified to show that 0 equals d. Next, we look at the coefficient of x to the 1, or in other words, x, which shows us that 1 equals a plus 4c plus 2d, but we already know that both c and d are 0, so this can be simplified to show that 1 equals a. And finally, if we look at the coefficient of x to the 0, which is just another name for the constant term, that shows us that -3 equals b plus 4d. And knowing that d equals 0, this simplifies to negative 3 equals b. And now we're ready to form our conclusion. We predicted this as the form of our PFD, and we found these values of the unknown constants. Now, since both c and d are 0, this second term may as well disappear entirely, leaving us with this incredibly amazing result for our PFD. This was a lot of effort just to show that something is equal to itself. So let's think about why this happened so that maybe we can avoid wasting our time in the future. If you look at the function that was given in the question, you'll notice this is of the form linear over irreducible quadratic squared. Does that sound familiar to you? It should sound familiar because this literally already matches the definition of a partial fraction. And if we take a partial fraction and try to decompose it into partial fractions, of course nothing is going to happen. So as a tip for the future, anytime you're thinking about forming a PFD, the very first thing you should do is check whether or not what you're looking at is already a partial fraction. Because if it is, you might be wasting a huge amount of time to accomplish nothing, and we don't want to do that. All right, here's one last example. Pause here and see if you can find this PFD on your own. And if you're ready to look at the solution, let's continue. First of all, notice that this is proper and it is not already a partial fraction, so we wouldn't be wasting our time in going through all the details. So we can go ahead and factor the denominator. After that, you'd be ready to proceed to the prediction step. Each factor in the denominator will provide us with one partial fraction because each factor is only raised to the power of 1. Now, my first fraction came from a linear factor, so it should have a constant numerator. My second fraction came from an irreducible quadratic factor, so it should have a linear numerator. That completes our prediction. So next, we can eliminate the fractions by multiplying our common denominator to both sides, just like always. You can pause and check that this would be the result. And at this stage, we actually now have two options. You can either plug in easy x values, or you can expand and compare coefficients. I actually like to use a combination of both methods. I do see that x equals 0 would make one of these terms disappear, so I might as well plug that in to start with. So pause and check that that would give me 2 equals a as a result. And now there aren't any other x values that would make terms disappear, so this is where I would normally expand and compare coefficients. Although if you prefer to just keep plugging in more x values, that is technically fine too. Before expanding, where I see an a, I might as well put a 2 instead, since I know that value now. So then you can go ahead and expand, collect like terms, and pause and check the details if this is going too fast for you. And now we're ready to do our comparison. The coefficient of x squared shows that 2 plus b equals 2, so with some basic algebra, we find b equals 0. The coefficient of x shows that c equals 1, and with that, we've found all of our constants. With all this information, we're ready to form our conclusion. So just plug in these values of a, b, and c, and we're finished. That's all for partial fractions, so I'll wrap things up here, and I'll see you next time.